Hello, my name is Lee Babi, and this is a presentation of the poster for our paper Big Code Doesn't Equal Big Vocabulary, Open Vocabulary Models for Source Code, which we worked on together with Rafael Karabatsis, Roman Robb, Charles Sutton, and Andrea Yanis. In our work, we address the issues of closed vocabulary language models by proposing to use byte pair encoding for corpus preprocessing. This enables building a neural language model of code, which is open vocabulary. Language models predict the next token given the context. In software engineering, apart from code completion, which is their direct application, they can be used to solve a variety of other tasks related to writing and maintenance of source code. For example, recommendation of identifier names, comment generation, and others. Closed vocabulary models can only predict tokens from a fixed vocabulary calculated on a training set in advance. That is why they struggle to predict long compound identifiers, which are often present in source code. One reason is that most such tokens are out of vocabulary, OOV for short, meaning they simply don't exist in the training set, and therefore they cannot be generated by the language model. Another issue is that despite not being out of vocabulary, many tokens are seen very few times during the training, which is not enough to effectively update the weights and train the embeddings. Most importantly, due to the freedom that developers have in creating identifiers, the vocabulary grows fast with the increase of the training corpus. This makes training such models memory and time intensive, and even impossible when scaling to larger training corpora, as was shown by Helendon and Devanboom. In our large-scale vocabulary study, we showed that the vocabulary grows linearly and exceeds 11 million tokens for around 13,000 projects. The OOV rate is extremely high, and the majority of tokens are infrequent. We have analyzed a number of modeling choices, however most of them only mitigate the vocabulary issues, but do not solve them. One of them is splitting tokens by camel case and snake case conventions, which results in the drastic decrease of vocabulary size and OOV rate. However, the vocabulary size of around 1 million is still too large. An approach that meets our needs is byte pair encoding, BPE for short, which was used for the first time in machine translation by Zenrich and now used in many state-of-the-art neural language models in NLP. With BPE, the vocabulary size can be specified as an input. The algorithm then works as follows. It starts with the vocabulary, which is a set of all characters in the corpus. Until the vocabulary reaches the specified size, at every iteration, BPE merges sequences of characters that occur most often to form new vocabulary entries. Resultant tokens are frequent, and there are no OOV. As the next step, we train a language model for source code. This model is open vocabulary. However, to predict a full token, it needs to predict multiple subtokens, for which a variant of the beam search is used. Our model uses such features as cache mechanism and dynamic adaptation to adapt to new projects. We perform an extensive evaluation of our model on the tasks of next token prediction and bug detection. We compare it to different n-gram models from the previous work by Helendon and Devanboom, as well as to the closed vocabulary model and the model trained on tokens split by conventions. Our model is superior in the majority of scenarios. We see these trends on Java, Python, and C corpora for 3 different vocabulary sizes. Since BPE allows us to scale to large amounts of data, we evaluate how our model can take advantage of it. For Java, for example, we compared the performance of the model trained on 107 projects. This is the largest amount of data that was used to train a neural language model of code so far, and the one trained on more than 13,000 projects. We see that our model can take advantage of a big corpus. As for implications for software engineering, first, our vocabulary study results can be used for building not only language models, but also other machine learning models for which large amounts of source code needs to be pre-processed. Second, high-performing pre-trained language models that we provide as artifacts open the doors to transfer learning and improve performance on downstream tasks with little or even no fine-tuning, and as a result, building better tools for software engineers. There are multiple directions for future work, some of which are considering algorithms that are alternatives or improvements of BPE, making use of the structure of source code as opposed to considering code as sequence of tokens, looking into other architectures like Transformer, which has become extremely popular in NLP lately, and larger capacity models to see what improvements they could bring. To summarize, we have shown that big code does not necessarily mean big vocabulary if the right vocabulary model and approach is chosen. Inspired by this, we built a neural language model for source code which can scale to large training corpora and outperforms corresponding closed vocabulary models. Thank you for your attention, and please make sure to take a look at our full paper as well as the GitHub repository, which contains links to the artifacts we provided, such as the corpora we used, the trained models, and the code to run the experiments. Thank you.